Okay, so let's do question 9 now. First part is just a bit of trapezium rule. Now, trapezium rule, just to remind you of the formula, it's area roughly equals strip width over 2 ends plus 2 times middles. Now, what does all that mean? Well, it simply means with any of these questions, you need a table of values, x and y, and we're dealing with the function y is e to the square root of x. Now we're trying to do this from 4 to 9, and they want us to do 5 strips, yeah? So if you think about it, 4, 5, 6, 7, 8, 9. Remember what I said about there'll always be one extra ordinate compared to number of strips, but there will be 5 trapezia there, yeah? So you'll need 6 ordinates for 5 trapezia, and in general, n plus 1 ordinates for n trapezia. We can work out our corresponding y values, e squared, e to the root 5, e to the root 6, e to the root 7, e to the root 8, or 2 root 2, or e to the 3. And we're just simply going to put those in our formula. So the area roughly equals, right, strip width, that's just the gap between any x ordinate. So it's going to be 1 in this case, so that's first bit's going to be a half. Ends, that's just the one at the start and the one at the end, and you add them together, and then plus 2 times the middles, which are also going to be adding together. So e to the root 5 plus e to the root 6 plus e to the root 7 plus e to the root 8. It's then a job for Mr. Calculator, plug it all in, and you should get 65.69 corrected 2 decimal places. Hope that makes sense. Okay, for the second part, we're going to need some difficult integration. Okay, and it's my theory actually, in these kind of questions, they often get you to do trapezium rule with integration, so that those people who haven't got a super duper calculator actually have a way of knowing whether their answer is probably correct or not. But we're integrating between 9 and 4, e to the root x dx, and they've given us a substitution, which is kind, which is u is x to the half. In any integration by substitution, differentiate first, half x to the minus a half. Now that's the same as saying x to the half du is a half dx, because that is in fact 1 over x to the half. So you can times the x to the half over. But that's the same as saying u du is going to be the same, or 2u du, if you like, is going to be the same as dx. So it's telling me how I can swap things. Now, the best way to do this is definitely to use your limits. Remember, these are the limits for x. Change them, I mean, not just use them, but change your limits if you're doing a substitution. It makes it easier. It genuinely does. So this is going to be 3 and that's going to be 2. I'm going to trade out the dx for a 2u du, and I'm still going to be left in there with e to the u. Okay, that's the substitution done. Now, what comes next? Well, I'm afraid it's by parts, because in general, if you've ever got x sine x, x cos x, x to the e, x e to the x, x ln x, yeah, these are all classic by parts ones, yeah. So ln, that's supposed to say, all of those, you know, you just recognize them. Oh, I need by parts for this. Now, how do you know when to use by parts? Well, how do you know when to do any kind of approach for integration? It really feels like a bag of tricks integration. I wish it were not like that, but it really does. Now, what we're going to have to do, I don't really like using, because you know the integration by parts formula, it has u's in it, doesn't it? So you can't say let u equal u. It doesn't feel right. So it might even be worth kind of writing this down as p e to the p dp and then saying u dv by dx. I might do that actually. Or let's just say that this is the same, yeah, because we could use a substitution, let u equal x, but let's just write it all in terms of x, just so it's a little bit easier to see how the by parts formula is going to work. Okay, so we're going to have to, I'll scribble those out. Sorry, you know what I'm like, I just write anything down. Let u equal x and dv by dx equal e to the x. Then du by dx is going to be 1. And v is going to be e to the x. So this is going to be equal to 2, open bracket, uv, so that's x e to the x minus the integral of v times du by dx, so e to the x dx. Now you can do the limits separately, or you can do it all together. I prefer doing it all together. So I'm going to have x e to the x minus e to the x between 3 and 2, which is 2 times, okay, that's going to be 3e cubed minus e cubed minus 2e squared e squared. Yeah, 2e squared minus e squared. Good, just checking that. You know what it's like, it's so easy to make a mistake here, so be careful. 3e cubed minus e cubed is 2e cubed. Times it by 2, you're going to make 4e cubed. And then 2e squared minus e squared is just e squared. You're taking away that e squared, but then you're timesing it by 2, so minus 2e squared, and you're done. Now, quick tip, at the end, what I would do in an exam is I'd check that that was very close to my calculator answer for part A, because trapezium rule is an estimate of that, and if it is, then I know it's right. But that's really only a tip for people who haven't got good calculators, because if you've got a good calculator, you'll know that's right. Okay, let's try number 10 now. What do we got for number 10? Oh, a bit of trig, love a bit of trig. Okay, so we've got a very standard kind of like part A here, nothing really weird going on here, and I'm sure you will have seen me do this. You can almost do this in your head. Sine of A plus A, in other words, you let B equal A in the compound angle formula, is sine A cos A plus sine A cos A. So sine of 2A is 2 sine A cos A, as required. I must admit, I almost feel like I'm not writing enough working down for that. They just want a demonstration that you're well aware of the compound angle formulae. You could even explicitly say let A equals B, write down the compound angle formula and then say let A equals B, and then it's pretty obvious where you've got it. But I think that should be enough to get full marks. It's pretty obvious what I've done. Show that questions are tricky though. Show that and prove questions. You've got to be slightly careful. Okay, let's actually get rid of that. That's pretty easy. I'm sure you won't be worried about that bit of working. Let's try part B. This looks a little bit harder. And it's a show that question, so you must show all your working. Okay, show that ln of tan of a half x is cosec x. Ooh. Okay, why not let y equal natural log of tan of a half x? How would I like to do this? You know what? I might even exponentiate both sides. Do you mind me exponentiating and using implicit differentiation? It just is crying out for it, really. This is my cheeky way of doing it. I'm going to go e to the y is tan of x over 2. And now what I'm going to do is I'm going to do d by dx to both sides. So I'm going to differentiate the left-hand side with respect to x. Well, the only way I can do that is by differentiating with respect to y and timesing by dy by dx. And then I'm going to differentiate the right-hand side with respect to x. Now, tan theta differentiates to sec squared theta, and I believe that is in the formula book. So tan of x over 2 is going to differentiate to a half sec squared of x over 2. And that's done. And now we need to find dy by dx. Remember, because we want dy by dx here, we want to show that ln of tan x over 2 differentiates to just cosec x. So that's what I've got to do. So I'm going to, once again, I'm going to write dy by dx equals, okay, a half sec squared x over 2. But then I've got to divide that by e to the y. But the thing is, I know what e to the y is, because e to the y is tan x over 2. So I've got a half sec squared x over 2 divided by tan of x over 2. Now, my immediate thinking is with, when I see sec squared and I see tan, is that 1 plus tan squared is sec squared. That might be useful. What am I trying to show here? I'm trying to show it's equal to cosec x. Actually, I'm now thinking double angle formulae would be quite handy here. Remember, cosec x is just 1 over sine x, yeah? Maybe it might be, what am I thinking? Let's write it out like this. Let's write it out as a half. Leave that half alone because hopefully it will sort itself out. Hope for the best, as they say. Sec is 1 over cos, isn't it? So we've got 1 over cos squared x over 2. Apologies for my tiny writing here. Divided by sine x over 2 divided by cos x over 2. Okay, well, if I multiply top and bottom here by cos squared x, I'm going to be left with the following. I'm quite excited now, actually. Can I just work over here, just because I'm running out of road here? Okay, let's leave the half outside. If I times top and bottom by cos squared x over 2, top and bottom, so I'm really timesing it by 1. I'm not changing the value of it. What am I going to get? I'm going to be left with 1 on the top, which is great, gets rid of the fraction, and then I'm going to be left with sine x over 2 cos x over 2. Ooh, I very much like that, because that is double angle, or almost double angle for sine, isn't it? Recall that sine 2x is 2 sine x cos x. And so sine x is 2 sine x over 2 cos x over 2. And if I multiply through that half into it, that's exactly what I've got. So this is in fact the same as 1 over sine x, which is cosec x. Yeah, congratulations. We did it. That's quite a tricky question. You know what I mean? You feel like you're going skew with. I was tempted to use a 1 plus tan squared is sec squared there. You can always get to the answer that way, but it might take you maybe slightly longer. Maybe you saw a much quicker way of doing it. Let me know in the comments if you found a much quicker way, and laugh at my methods. Feel free to do that. I don't mind at all. Okay, so let's get rid of that. Let's do part C. Okay, what are we on? Ooh. Find the x-coordinates of the points on C where dy by dx equals 0. Okay, so let's have a little think about this. We're going to need to differentiate it naturally, that function. So we'll differentiate it. Let's have dy by dx. Okay, we already know the first bit differentiates to cosec x, which is 1 over sine x. And the minus 3 sine x is going to differentiate to minus 3 cos x. And we're trying to find where that equals 0. Okay, I think my preferred way of doing this would be, oh, note, by the way, we're only working in the range from 0 to pi. Bear in mind all those kinds of things. But straight away, I'm going to bring the 3 cos x over there. And I'm going to times sine x over. And I really like the look of that, because that's the same as, remember that 2 sine x cos x is sine 2x. And so 3 sine x cos x will be 1.5 times that. So it'll be 1.5 sine 2x. And that's what I'm going to use. 1 equals 1.5 sine 2x. And so sine 2x is 1 over 1.5, which is 2/3. You see, that is an equation which I can solve. I can do inverse sine of 2/3, but it does mean, once again, somewhat annoyingly, I'm going to have to reach for my calculator. Inverse sine of 2/3 gives me 0.7, what is it, 3 decimal places, 7, I'm going to write to a few, actually, 9, 7, blah, blah, blah. And don't forget, please don't divide by 2 yet. Use your rule of thumb. 180 minus for sine. Oh, but we're in radians, so we're going to do 2 pi, sorry, pi, pi minus that, and that gives me 2.4119. And then at the end, halve those, and you get 0.3 How many doing it? 0.365 or 1.206. And those are the final answers, I hope. Let me just check I've got the answer on the other screen. I think that's right. Yeah, it's right. Cool. Okay. Well done. Keep watching. And yeah, let me know if you've got any questions in comments or just email me.